Let's look at some properties of inner product spaces, ultimately leading to the definition of Hilbert space. That'll be the last thing we see in this section of notes, in fact. A Hilbert space is, to kind of give it away up front, it's a complete inner product space. So we need to address inner products. We do so in section 4.2 by addressing semi-inner products. So much of this section relates to semi-inner products and induced semi-norms. It's really the inner products themselves that we're interested in the setting of the Hilbert spaces. So we'll define inner products in this section and state a number of results. Most of them are not very complicated, and most of them have a bit of a geometric interpretation to them. So formally, a semi-inner product on a complex linear space X. So remember, we're taking our scalars to be complex in this chapter. Semi-inner product is a mapping from the Cartesian product of X with itself. So it takes pairs of vertices, pairs of vectors, and associates with them a complex number. So we'll denote that complex number with angle brackets. So the inner product of X with Y is denoted with these angle brackets. And we require for any pair of vectors, X and Y in particular, and any vectors in general, X, Y, and Z, and for alpha as scalar, that the inner product satisfy the following conditions. So it's linear in the first position, the first variable. That is, if we have an inner product of X plus Y with Z, that complex number equals the sum of the following two complex numbers, the inner product of X with Z plus the inner product of Y with Z. So we've broken it up over the vector addition sign in the first variable, as they say. And if we have scalar alpha times X in the first position, the inner product of alpha X with Z is the same as alpha times the inner product of X with Z. So we can bring scalars outside of the inner product when they're in that first position. We didn't say anything about the second position, but we will, and it's a tiny bit more complicated, and this is where the scalars being complex will play a particular role. We require conjugate symmetry. The inner product of Y with X is the conjugate of the inner product of X with Y. So that will combine with the first property will allow us to deal with linearity ideas in the second component of the inner product. More of that shortly. And we require positivity that the inner product of X with itself is greater than or equal to 0. The fact that we've stated it in terms of an inequality implies that it's a real number as well. So it's a non-negative real number. Now, what we're not requiring in a semi-inner product that we will require in an inner product is the fact that the inner product of X with itself equals 0, implying that X is a 0 vector. In a semi-inner product, we don't have this condition. In an inner product, we do have this condition. So an inner product is a semi-inner product satisfying these three conditions, along with the condition that the inner product of X with itself equaling scalar 0 implies X must be the 0 vector. A linear space with a semi-inner product is called a semi-inner product space, and you can drop the semis. A linear space with an inner product is called an inner product space, and it's inner product spaces that we're interested in. This first property, linearity in the first variable, of course, we can combine the vector addition and the scalar multiplication to read alpha X plus beta Y inner product with Z is alpha inner product of X with Z plus beta inner product with Y with Z. Combining the scalar multiplication property and the vector addition property. Now, about the second entry in the inner product, if we were to take the inner product of Z with alpha X plus beta Y, well, we could reverse the order of that inner product and take the inner product of the linear combination with vector z, but that requires us to introduce a complex conjugate, as part B of the definition of semi-inner product says. So what we could do is insert a conjugate, reverse the order by property 2, then use the linearity, because then we would have the linear combination inside the first component of the inner product. So then use the linearity there, and then swap the orders back, introducing a second conjugate, returning the inner products to the original values. But along the way, we've picked up conjugates on the scalars. So there's a couple of steps omitted here, but this is how things are dealt with in terms of the second component and linear combination. And sometimes a semi-inner product is said to be conjugate linear in the second variable. So we can still break it up over linear combinations, but scalars come out of the second component with conjugates on them. So this is the property of conjugate linearity. A bit of a warning, not everybody treats inner products the same way. In some cases, they're taken to be linear in the second variable and conjugate linear in the first. I think in the physics settings, this pops up a lot in quantum theory. In the physics setting, there's a tendency to have the conjugate linearity in the first variable. So this isn't entirely universal, so just be warned. We will treat it as defined with linearity in the first term and conjugate linearity in the second. All right, a semi-inner product can be used to define a semi-norm. So we need to talk a little bit about semi-norms. It's come up in passing in the book, mostly in exercises, but more on a semi-norm in a second. But in particular, inner products induce norms. We'll take the norm or the semi-norm of vector x to be the square root of the inner product of x with itself. Remember, even in the semi-norm setting, the inner product of x with itself is a non-negative real number. So when we take the square root of it, of course, we mean the positive real square root. So for norms, we're still getting out, or alleged norms at this stage, we're still getting out something that is a non-negative real number. So the norms are non-negative real numbers, semi-norms are non-negative real numbers. We need to confirm that all the properties of a norm or semi-norm are satisfied. So by saying norm or semi-norm for that matter, that's in question at this stage. We'll establish that these really are norms and semi-norms. It's easy to show that the semi-norm of alpha x is the modulus of alpha times the norm of x. Modulus, recall, absolute value, if you like. Some people call modulus absolute value, but the scalars are complex in this setting. So if we take the norm or semi-norm of alpha x, by the definition we just had, that would be the inner product of that vector with itself, square root of. We can bring the scalar in the first variable out. We can bring the scalar in the second variable, second position out, but it comes out with a conjugate. So we get alpha times alpha conjugate. Well, that's the norm of alpha squared. The square root symbol will produce the square root of alpha. You're left with the inner product of x with itself, and that by definition is the semi-norm of x with a square root. So we get scalars to come out of semi-norms induced by inner products as they should. The scalar property holds for this alleged semi-norm. If we have an inner product, then the norm of x equals 0 if and only if x is a 0 vector. That will follow by the little additional property that the only time the inner product of a vector with itself equals 0 is when you have the 0 vector. So down here, we're getting a norm of 0 if and only if we deal with the 0 vector. That is a norm induced by an inner product, not a semi-inner product. But a semi-norm is, by definition, a mapping that satisfies all the properties of a norm except the property that norm of x equals 0 implies x is a 0 vector. So semi-norms have non-zero vectors that have semi-norms of 0. So there's other vectors out there with a semi-norm of 0 other than just the 0 vector. That's the semi in semi-norm. So, I mean, one of the problems with this is I could have the semi-norm of x minus y equals 0, and yet x and y be different vectors. They must not be very different vectors, though. But that's what a semi-norm is. You have the scalar property, you have that it's non-negative real valued, and you have the triangle inequality. You just don't have this little property here. Exercise 2.6, back in chapter 2, gives some properties of semi-norms. So we're not interested in semi-norms, and we're not particularly interested in semi-inner products either. We're interested in inner products and norms. But this section is laid out in terms of semi-inner products. So in the rest of this section, if we refer to a semi-inner product space, then it's understood when we use these symbols, they represent the semi-norm induced by the semi-inner product. So the statements are a bit more general than we actually need for our purposes. Our purposes are Hilbert spaces, which are complete inner product spaces, not semi-inner product spaces. Of course, every inner product space is a semi-inner product space. So things we say about semi-inner products also hold, and maybe more, for inner products. For Cn, we take the linear space to be Cn, so complex scalars in dimensions. Then the inner product of an n-tuple of complex scalars with a second n-tuple of complex scalars is sum from k equals 1 to n of x sub k times y sub k conjugate. So you have to conjugate the components of that second vector. And that conjugation with the second vector will yield the conjugate linearity that we were talking about before. If we were to deal with Rn, and we could do a similar type thing, we wouldn't need the conjugate because there's nothing to conjugate if we deal with real numbers. But this inner product stuff, of course, in the real setting, reduces down to just the usual old dot product stuff. In the complex setting, it's the usual old dot product that you'd have on Cn. You'd have to put conjugation in this and take that dot product computed as such. And you get complex numbers out in general. When you use the norm induced by it, then you get the usual behavior that you'd expect from Cn. Not surprisingly, if we take two functions, f and g, from L2, an inner product on L2 is given by integrating over whatever set fg conjugate. Again, second position, here we go, second position implies some conjugation to get that conjugate linearity stuff. So were we to deal with function spaces, and we will, because a lot of good stuff happens in function spaces, then there'd have to be some conjugation somehow introduced there as well. And in the function spaces, the inner products are accomplished by taking integrals. Well, we foreshadowed this because we've looked at the LP spaces as normed linear spaces. We just didn't have the norms coming out of inner products. And it turns out that that idea of having an inner product that induces the norm or semi-norm only works for LP spaces when p equals 2. More of that shortly. We're developing the equipment to show that. Lemma 4.2 is a so-called basic identity. Says let X be a semi-inner product space. Then the semi-norm induced by the semi-inner product satisfies the following. For all vectors x and y, we have x plus y, semi-norm squared, equals semi-norm of x squared plus semi-norm of y squared plus 2 times the real part of the inner product. Let's go through proof of that. Quite straightforward. Okay. Well, when we write these norm symbols, they're semi-norms because we're in a semi-inner product space, but you know what these symbols represent: the inner product of a vector with itself. square root of, but we've got the squaring on there. So if we take the semi-norm of x plus y squared, that's the inner product of x plus y with itself. You know linearity properties of semi-norms by definition. We've got linearity in the first term, so we can expand this out using the linearity in the first variable in the first position. We've got x plus y in the second position in both of these. We've got linearity there as well. There's no scalars involved, so no conjugations necessary to this point. So we've simply expanded it over the vector addition in the first position and the second position to produce this. Hey, there's a semi-inner product of x with itself. By definition, that's the semi-norm of x squared. Semi-inner product of y with itself, well, that's the semi-norm of y squared. And here we've got an inner product of x with y, and here's an inner product of y with x. So let's use that conjugation property and reverse the orders. Write this as the conjugate of the inner product of x with y. Reverse the orders, introduce a conjugate. Elementary properties of complex numbers. If you add any complex number, and this inner product is a complex number, you add any complex number to its conjugate, the imaginary parts disappear and you get twice the real part. So this summation yields twice the real part of that complex number, twice the real part of the inner product, and that's all that was claimed. So there's a proof of the so-called basic identity. In Rn, you see similar things. You'd establish something like this in Rn. What you would pick up here would relate to the dot product. And the dot product would be real, so you wouldn't need the real stuff. You get twice the dot product as this little term added on to the side. Reminds me a little bit of the Pythagorean theorem, of course. And in Rn, it certainly is related to the Pythagorean theorem. What happens is this term here is related to the angle between the vectors in Rn. So there's the basic identity. We'll use that in several of the following computations. First, we've got the Cauchy-Schwartz inequality. Quick passing note, Promislo spells Schwartz with a T, and I think it's more common to omit that T in the Schwartz part of the Cauchy-Schwartz inequality, sometimes called simply the Schwartz inequality. Anyhow, the main interest in the Cauchy-Schwartz inequality is to prove the triangle inequality. You do this exact same type of thing in sophomore linear algebra. Probably you're not dealing with complex scalars there, but you go through and you establish the Schwartz inequality or the Cauchy-Schwartz inequality, and you use that to establish the triangle inequality. So we're up to the same thing. Given a semi-inner product on space X, for all x and y vectors, we have that the modulus of the inner product of x with y is less than or equal to the norm of x times the norm of y. If, in addition, this semi-inner product actually is an inner product, so it comes with that extra little condition about zero vectors, then equality holds if and only if x is a scalar multiple of y. That is, x and y are linearly dependent. Easy to describe the linear dependence of two vectors. One's a scalar multiple of the other. Let's go through proof of that. This is lengthier than some of the arguments in here, but it's making several claims. First, we can scale x and y in this little Cauchy-Schwartz inequality, and that doesn't change anything. If we were to take vector x, for example, and multiply it by some scalar alpha, well, you could bring the modulus of alpha outside of that norm. You could also bring that alpha outside the inner product by linearity in the first term, and then bring it outside the modulus on that side. You'd pick up a modulus of alpha on both sides, and you could cancel them. Similarly, we could multiply y by some scalar beta, and ultimately get cancellation of the modulus of beta. A little bit more complicated with the y's because we get that conjugate linearity thing. We'd pick up a modulus of beta bar, the conjugate of beta, but that's the same as a modulus of beta. So we're going to freely scale these vectors x and y. For example, we'll normalize one of them somewhere along the line, and that won't change the claim at all. It simplifies the proof. Scaling, the scaling factor is introduced on both sides and divided out. So that's just the fact I can get scalars outside of both sides. So we freely scale vectors. Suppose vector y doesn't have semi-norm 0. So initially we're operating under semi-norms. Once we get the Schwartz inequality established for semi-norms, then we'll talk about the equality and the inner product. So first, assume the semi-norm of y is not 0. If the inner product of x with y equals 0, we're done. The left-hand side is 0, the right-hand side is non-negative, we're done. If the inner product of x with y is not 0, and y is not a vector with norm 0, then x and y can be scaled so that y has norm 1. So we're normalizing vector y. We can do that as long as it's not the 0 vector. And then we can scale the inner product x and y. If it's not 0, we can scale it in such a way that we convert the inner product of x and y to make it 1. What we're doing here is scaling vector x. We'd have to scale vector x maybe by complex factor, because remember that inner product is going to be complex. So what we're doing here is scaling vector y to make it a unit vector and scaling vector x so that the resulting inner product is 1. That can be done. It changes the vectors, but it changes them by factors that don't affect the behavior in the sense of the Schwartz inequality, Cauchy-Schwartz inequality. All right, Lemma 4.2, the elementary identity, basic identity, we called it. Apply that, but take y and replace it with negative y. We had x plus y, norm, semi-norm squared. Replace y with negative y. So we get x minus y, semi-norm squared. Semi-norms are non-negative, so we put a 0 over here. 0 is less than or equal to this semi-norm squared. And the semi-norm squared equals the semi-norm squared of the first vector plus the semi-norm squared of the second vector plus twice the real part of the inner product of those two vectors. So this is exactly Lemma 4.2, but we've replaced y with negative y and picked up a negative sign there, there, and there. Well, we've taken y to have semi-norm 1, so negative y also has semi-norm 1. The semi-norm absorbs a scalar, has a scalar property. And the norm of y is simply 1, so we pick up a 1 there. Here, we've got a negative sign inside the inner product. We can bring that negative sign outside of the inner product. We could even bring it outside the real part. But no problems there. We need to conjugate when we bring scalars out of the second position, the second variable, but it's real. Negative 1 is real to start with, so that changes nothing. But we can bring the negative outside. The inner product of x with y, things have been scaled so that that's 1. So the real part of this inner product produces a negative 1. Negative from this, which we bring outside, and then the real part of the inner product is 1 itself. So we've picked up a negative 1 there. We've got norm, semi-norm of x squared plus 1 plus 2 times negative 1, which is exactly what's written here. We've got the norm, semi-norm squared of x minus 1. But that, as we observed, is greater than or equal to 0, so it must be that the norm of x is greater than or equal to 1. Then the result holds in this case, because in that case, we've got the inner product is 1, so we'll have a 1 on this side of the equation. We had normalized vector y, so it has norm 1, so we have a 1 there. And we just showed that the norm, semi-norm of x is greater than or equal to 1, so this number is greater than or equal to 1. And this reads 1 is less than or equal to a quantity that's at least 1, and that's true. So the case holds in the event that vector y is non-zero. Symmetrically, we could interchange the roles of x and y. that would affect nothing in the claim here. The conjugation that would appear when reversing the order of the inner product is absorbed by the modulus. So if x is a zero vector as well, then this holds. In other words, we've established the Cauchy-Schwartz inequality in the event that either vector x doesn't have norm zero or vector y doesn't have norm zero. So we have established the Cauchy-Schwartz inequality in all cases, except the case where both x and y have semi-norm zero. Am I saying semi every time? Probably not. But if the semi-norm of y is not zero, we're done. If the semi-norm of x is not zero, we're done. If the semi-norms of both x and y are zero, that we haven't shown yet. Not surprisingly, it holds then as well. So we need to address the case when the semi-norm of x and the semi-norm of y are both zero. But the inner product is not zero. Remember, the result holds trivially when the inner product is zero. Then we can scale x and y such that the inner product of x and y equals 1. Again, scaling can be done. We're not saying that these are zero vectors. We're saying that they have semi-norm zero. This wouldn't happen if we had norms. Remember, in a semi-norm, there are vectors that have semi-norm zero that may not be the zero vectors. We're not scaling the magnitudes of the vectors. We're scaling the inner product using the linearity properties. So scale x and y such that the inner product is 1. That can be done even if these vectors have semi-norm 0. Lemma 4.2, the basic identity then tells us the semi-norm of x minus y squared equals the semi-norm of x squared plus the semi-norm of negative y squared plus twice the real part of this inner product. Same thing we had on the previous slide, but this time we have the norm, semi-norm of x equal to 0 and the semi-norm of y equals to 0. So both of these are 0. That leads us to 0 plus 0 plus. We've scaled things in such a way that the semi-inner product of x and y equals 1. So we'll pick up a 1 from this. Well, a 1 from the inner product of x with y. The negative comes out again as it did in the previous argument. We've got the 2 up front. This simplifies to 0 plus 0 minus 2. And what we've got is 0 is less than or equal to negative 2. That can't hold. Actually, it must be the case that the inner product of x with y must be 0. There's a tiny little lemma about semi-inner products. If we take the semi-inner product of two vectors which have semi-norm 0, then that semi-inner product must be 0. This semi-norm, semi-inner product stuff I think of as kind of laying on a layer of uncertainty with these vectors that have norm 0. They're not the 0 vector. They're vectors with norm, well, semi-norm 0. But we've established then the Cauchy-Schwartz inequality. This takes care of the case where x and y both had a semi-norm of 0, and the previous slide takes care of the case where at least one of them does not have semi-norm 0. So we've established for a semi-inner product, we've established the Cauchy-Schwartz inequality. Now let's change gears. So we're switching over now to considering an inner product. So now, if we come up with something with a norm of 0, it's the 0 vector. That's a property of inner products. So we need to address the fact that if we have an inner product, then equality holds. That is, this inequality becomes an equality if and only if x is a scalar multiple of y. That is, x and y are linearly dependent. If and only if, all right, suppose y is a scalar multiple of x. I think that's the easy part. We get the modulus of the inner product of x and y to be the modulus of the inner product of x with alpha x, because that's what y equals. We can bring alpha outside of that inner product. Came out of the second position, so it comes out with a conjugate on top of it. The modulus of the product is the product of the moduli. So this comes out as the modulus of alpha conjugate, which is the same as the modulus of alpha. So we do get the modulus of alpha on the outside. Here we've got the inner product of x with itself, which, by the way, we know that to be non-negative. So the moduli don't affect anything on that. So I guess it'd be absolute values of real numbers in that case. But what the inner product of x with itself is the norm of x squared. So I can't say norm this time. I don't have to be so conscientious about semi-norms. Since we have an inner product, these are actual norms. And we can split that up in a suggestive way. Let's write it as the norm of x times the modulus of alpha times the norm of x. And let's take the scalar property on the norm and put this alpha inside. So we'll have the norm of alpha x, and that's y itself. And indeed, the modulus of the inner product equals the product of the norms, as we would expect. So if y is a scalar multiple of x, then Schwartz's inequality reduces to equality. Just between you and me, for some intuitive feel of why this is happening, remember, the inner product deals with the angle between vectors x and y. At least it did in sophomore linear algebra. And what we're getting then is the inner product equals the product of the lengths of the vectors, having some implication about the angle between those vectors. I think this was related to the cosine of the angle between the vectors, and that cosine is its biggest when that angle is 0. In other words, when vectors x and y were scalar multiples of each other. Okay, the angle's 0 or pi. So parallel or anti-parallel is how you would speak in sophomore linear algebra. So there's actually geometry behind this as well. But if we have a scalar multiple, then we get equality. They said if and only if, if and only if. So we need to reverse that and assume we have equality and show that implies the scalar multiple situation. So suppose equality holds. That is, we've got vectors x and y such that the modulus of the inner product equals the product of the moduli. Now, if we take the inner product of x with 0, the inner product of 0 and x in that order, let's write the 0 vector as x minus x. Let's use the linearity in the first term. Write that as the inner product of x minus itself. We get 0 out. It's just odd. We had never said this. So in an inner product, if we take the inner product of the vector 0 with any vector, that inner product will be 0. So if either the norm of x equals 0 or the norm of y equals 0, then x is a 0 vector or y is the 0 vector, right? We're dealing here with an inner product and the norm which it induces. So I can draw the conclusion with a norm that norm equals 0 implies x equals 0. So because we have a norm, not a semi-norm, we can draw these conclusions here. And if either of the vectors is the 0 vector, then we have linear dependence. One is a scalar multiple of the other. Yeah, one of them is 0 times the other one. So there's your scalar. So they are linearly dependent. So if the norms are both 0, then one of the vectors must be the 0 vector. The inner product is 0, and both sides of this equation are 0. That's equality. So we need to consider the case when both are non-zero. If either is 0, we've got equality. Suppose neither is 0. If neither x nor y is the 0 vector, then we'll do our scaling thing, similar to what we've done before. Normalize vector y so that it has norm 1. It's not a 0 vector, so you can do that, divided by its norm. And then scale x so that the resulting inner product of x with y is 1. Couldn't be 0, right? Right, because we're not dealing with 0 vectors here, so we can scale that. The equality in Schwartz's inequality then implies that the norm of x must be 1. So we have 1 on this side. We've got y as a unit vector, so a 1 here. The equality then implies that x itself must be a unit vector. We've scaled it to get this. That must have resulted in a unit vector. Now, if we go back to the basic identity, again, replacing y with negative y's, we've already done once or twice, we get the norm of x minus y squared equals the norm of x squared plus the norm of y squared plus twice the real part of this inner product. But we know x has norm 1, we know y has norm 1, so we pick up 1's in each of those places, 1 squared. The inner product was 1. Okay, we got the negative sign. We've been through this. You know, this is going to produce a 2 times negative 1. And what we get out then is 0 on this side. On the left-hand side, we had a norm squared. Norms and norm squares are non-negative real numbers, so we can introduce the 0 less than on this side. We've got an equals 0 on the right-hand side. Then this inequality in particular must be an equality. We squeeze things together like that so that we must have the norm of x minus y equals 0. And if the norm of x minus y equals 0, norm, then x equals y. If we had a semi-norm, we couldn't take this last step and draw the conclusion that y equals x. That's the reason the added hypotheses of inner product instead of semi-inner product were introduced in this equality conversation. Right there is where the semi-norm would break down. But norm allows us to draw that conclusion. So y equals x, but we were supposed to show y as a multiple of x. Well, we started with an original x and y, and then we scaled them. We multiplied them by scalars. So we've scaled the original x and y to get some scalar multiples of the original x and y. Well, collect those scalars together and we get x is a multiple of y. X equals alpha y for some alpha based on the 2 scalings that we did up here. And that's equality in the Schwartz's, Cauchy-Schwartz inequality. As commented earlier, you do this Cauchy-Schwartz stuff so you can prove the triangle inequality. You always do the Cauchy-Schwartz stuff so you can establish the triangle inequality. You do it in sophomore linear algebra. We're doing it here. You take a physics class where they're hung up on observation operators in quantum mechanics. And sure enough, here comes the Cauchy-Schwartz inequality. And what they're after a triangle inequality. If memory serves, don't tell anybody I said this because I'm speculating here. I seem to recall that the Cauchy-Schwartz inequality in the physics setting is related to the Heisenberg uncertainty principle. So it comes out somehow connected to that, if memory serves. But we're interested in Hilbert spaces. We want to make sure at this stage that the semi-norm induced by the semi-inner product really is a semi-norm, that in particular that it satisfies the triangle inequality. And it does, and the proof, with all the stuff we know, the proof is pretty easy. So the claim is, for X, a semi-inner product space, the semi-norm induced by the semi-inner product satisfies for any X and Y, the norm of X, the semi-norm of X plus Y is less than or equal to the semi-norm of X plus the semi-norm of Y. There's your triangle inequality for semi-norms. The proof goes simply as, let's take the norm squared we saw by expressing that in terms of semi-inner products. Did I say it correctly? The semi-norm squared. So we're back to that stuff. The semi-norm squared equals the semi-norm of x squared plus the semi-norm of y squared plus twice the real part of the inner product, the basic identity. We know the real part of the inner product is less than or equal to the modulus of that complex number. The real part is always less than or equal to the modulus. The modulus is the real part squared plus the imaginary part squared, square root of. In fact, we get equality here if and only if the imaginary part is 0. But properties of complex numbers, real part less than or equal to modulus of that complex number. The complex number is the inner product itself. So a little property from introductory elementary complex variables. The Cauchy-Schwartz inequality says, hey, the the modulus of the inner product is less than or equal to the product of the norms. So there's the Cauchy-Schwartz inequality. Here, the basic identity was easy, followed from the definition of the induced semi-norm. This is an elementary property of complex numbers, but to get this step, we needed the Cauchy-Schwartz inequality. So it becomes a necessary evil in establishing the triangle inequality. The cute thing that occurs and always occurs in these settings is, why, that's a perfect square. It's the norm of x plus the norm of y squared. Foil it out, you get the first one squared, you get the last one squared, and you get twice the product. So that's exactly what we have. Factors like that take a square root. Square root's an increasing function and preserves the inequality. Taking square roots gives a triangle inequality. So there you go. Triangle inequality, once you have the Schwartz inequality, follows easily. Okay, with the triangle inequality established and those other properties, the scalar property in particular, and the thing about the norm of zero vectors, whether it's norm or semi-norm, possibly produces a zero vector out. If the norm is zero, then the vector must be the zero vector in a norm, not in a semi-norm. But we've got all the properties of either norm or semi-norm respectively satisfied once we get the triangle inequality, and that was the hardest one. We see that if the inner product is a semi, well, if this is a semi-inner product, then it induces a semi-norm. If it's a regular old inner product, forget the stuff in parentheses, then it induces a norm. For our purposes, inner products induce norms. Same thing happened in RN. Same thing happened in sophomore linear algebra when you were dealing with dot products. And you saw that dot products were related to norms of vectors. You might have encountered norms of vectors before you encountered dot products. But anyhow, when you've encountered them both, you see how norms are related to dot products. So that's exactly what's going on here. We've seen at this stage a bunch of normed linear spaces. Rn, Cn, big L2, little L2. And in all of these, the standard Euclidean norms are induced by inner products. These are somewhat special cases. If we look at the LP spaces, and we've talked at some length about the LP spaces, we might have glossed over details because we're not assuming too much measure theory background, but we've mentioned the LP spaces in a section in chapter 2, I think it was, around the end. There's something special about L2, as we will prove. Of all the LP spaces, the only one that's an inner product space is P equals 2. In L2, the norm is induced by an inner product. In all the other LP spaces, the norm is not induced by an inner product. So there's something special about P equals 2. Big L2 and little L2. Both of those, if we look at the little LP space, is the only one that has the norm induced by an inner product is when P equals 2. There's something special about that. The Parallelogram Law actually will allow us to establish that claim that the only LP space, which is an inner product space, is when P equals 2. So they're all normed linear spaces. They're just not inner product spaces that induce a norm. The norm is not induced by an inner product except when P equals 2 in the LP spaces. That's a hell of a claim. We'll use the parallelogram law to establish it. So suppose X is a semi-inner product space, then the semi-norm induced by the semi-inner product satisfies the following conditions. So if we started with a semi-inner product and produced a semi-norm, of course it's not the semi stuff that we're interested in, then that semi-norm must satisfy this. If you got a norm that doesn't satisfy this, then it isn't a norm induced by an inner product or semi-inner product, is what we'll actually use this for. The proof for the parallelogram law. And we'll look at old pictures to why it's called the parallelogram law, but the proof is very straightforward. Lemma 4.2, the basic identity, said exactly this. If you replace y with negative y, we've been through this several times, it produces this. The negative comes out of the inner product and blah, blah, blah. The negative is absorbed there. Now, if you'll add these two things together, you'll get the norm of x plus y. You'll get the semi-norm of x plus y squared plus semi-norm of x minus y squared on the left-hand side, which is what we have up here. On the right-hand side, you'll pick up the semi-norm of x squared twice. You'll pick up the semi-norm of y squared twice. These two differ by a negative sign and cancel, and that produces the right-hand side. So this is just a little additional observation from the basic identity. So there's the parallelogram law. Let's look at the notes and see why in the world it's called a parallelogram law. A result from Euclid, so about 2,300 years ago, says if we have a parallelogram, then the sum of the squares of the diagonals equals the sum of the squares of the lengths of the four sides. The diagonals have, so we've drawn here, the length of this would be the norm of x plus y. The length of the red one would be the norm of x minus y. This has norm y, it's parallelogram. This side over here also has norm y. This side has norm x, it's parallelogram. The top also has norm x as its length. So if we'll add up the sums of the squares of the diagonals, that would be this norm squared plus that norm squared. Hey, that's exactly what we have up here. This norm squared plus that norm squared. X plus y, x minus y. That's what we have for the diagonals. I'm kind of borrowing a picture from R2 here. And then we would have the sum of the squares of the lengths of the sides. Sum of the squares of the lengths of the four edges. Norm of x squared plus norm of y squared plus norm of x squared again plus norm of y squared again. So that's exactly what you get. That's a property of parallelograms in Euclidean geometry, and that's the reason this is called a parallelogram law. As I kind of hinted at, the contrapositive of the parallelogram law might read, if the semi-norm in a semi-norm linear space does not satisfy the parallelogram law, then the semi-norm is not induced by a semi-inner product. This can be used to show that in the little LP spaces and the big LP spaces, that the LP spaces, these norm linear spaces for P between 1 and 2 excluding 2, and for P greater than 2, including infinity, the L infinity spaces, these are not normed linear spaces where the norm is induced by an inner product because they violate the parallelogram law. If they violate the parallelogram law, they're not related to a norm induced by an inner product. One of the exercises deals with the little LP spaces, and it similarly holds. I think there's proofs in the notes somewhere for capital LP spaces. The only ones of the LP spaces that are inner product spaces are the case P equals 2. The others are simply normed linear spaces. Okay, so we can express the norm in an inner product space, the norm induced by the inner product, we can express the norm in terms of the inner product. So can you do it the other way around? Can you express an inner product in terms of a norm? And here, the norm involves the inner product of the vector with itself. But could you express the inner product of x with y in terms of norms of x's and y's, and sums or differences of x's and y's maybe? That's what the polarization identity gives. So it's easy to express norms in terms of inner products, and it turns out you can reverse that procedure and express the inner product of x with y in terms of a bunch of norms. Let X be a semi-inner product space, then the semi-norm induced by the semi-inner product satisfies the following conditions. The inner product of X with Y is 1/4 this sum and difference of semi-norms squared. And we've picked up some i's along the way, it looks like. Let's go through proof of that. Also not complicated, it's a little bit longer. It's a more involved equation. But in the parallelogram law, we saw exactly these two things. It was the basic identity and then the basic identity with y replaced with negative y. We added these together, and that's where the parallelogram law came from. Let's subtract them. So if we subtract these from each other, let's see, on this side, subtract, we'd have semi-norm of x squared minus semi-norm of x squared. We lose this, we lose this. Here we're subtracting, we'll actually end up with 4 of these. There's the 4 real part of the inner product. And on the other side of the equation, we'll have this left-hand side minus this left-hand side. We're subtracting the 2, producing this equation. Let's call it asterisk. All right, how do you feel about that? It's got a 4 in it, and we got a 1/4 in the claim. So I'm sure that's where the 1/4 will come from. We'll do some division here at some point. But we've got 4 times the real part of the inner product expressed like this. We need the imaginary part of the inner product as well. Well, the inner product of x with y is the real part of the inner product plus I times the imaginary part of the inner product. That's what the real and imaginary parts of a complex number are. So we can take the imaginary part of the inner product, write it also as the real part of negative I times the inner product. And look what happens if you take a complex number and you multiply it by negative I. Stick a negative I in there. This is going to become imaginary when multiplied by negative I. You multiply this by negative I, you get negative I times the imaginary part. I squared is negative 1. This becomes the real part. So the imaginary part equals the real part of negative I times the complex number. Just an elementary manipulation of what real and imaginary parts mean. So we can relate real and imaginary parts in this sense. Now let's take this, that scalar goes inside. Let's put it in the second entry. It would go into the second entry, the second variable as an I. Remember, we've got conjugate linearity in the second variable. So the I would come out with a conjugate, and the conjugate of I is negative I. So that's the proper manipulation. Let's label that with a double asterisk. We've already got the real part of an inner product expressed in terms of some norms. So what we're going to do is use this to deduce the imaginary part of x, inner product of x with y, and relating it to this. What we're going to do is replace the y with an iy up here. And here will come some iy's, and notice the answer has some iy's in it. Maybe bounce back and forth between this slide and the next one if needed. So we'll use asterisk for the real part of I, and replacing y with iy. Here's asterisk. Here's what we get by replacing y with iy. It produces this. Notice we've taken the 4 to the other side now. We've got the real part of the inner product of x and y. Here we have the real part of the inner product of x with iy. Also notice here we've got exactly, here we've got exactly this in the alleged conclusion. Here's the semi-norm of x plus y squared minus the semi-norm of x minus y squared. We got that part there. This, we got the 1/4 factored out in the conclusion. This matches up with that. This matches up with that along with the negative sign. It's just missing the i's. Where's the i's come from? That's what star dealt with. Here we're looking at the real part of the inner product of x with iy. Let's go back to the previous slide. Star said the real part of the inner product of x with iy is the imaginary part of the inner product of x and y. Going forward. So if we write the inner product of xy as the real part of the inner product plus I times the imaginary part, this is the imaginary part, we pick up an I. in writing it as real part plus I times imaginary part. That's where the I comes from, substituting in there, and that's exactly what was claimed. Why they call it the polarization identity, I got no real insight on that, but think of it as a way to express inner products in terms of norms. When those inner products are induced by when the norm is induced by the inner product, or the semi-norm is induced by the semi-inner product, we can express the semi-inner product in terms of the semi-norms. Forgive me, I'm just not that interested in semi-inner products and semi-norms. Next result, we've really already hinted at, says if we have a norm on a complex linear space satisfying the parallelogram law, then the norm is induced by an inner product. The contrapositive of that's what we mentioned above. If we have a norm linear space where the norm is not induced by an inner product, then that norm does not satisfy the parallelogram law. And that's what we'll use to show that the LP spaces are not inner product spaces unless P equals 2. All right, a final little statement, just some general results related to semi-inner products. Says in any semi-inner product space, if the x sub n's converge to x and the y sub n's converge to y, then the inner products of x sub n's with y sub n's converges to the inner product of x with y. Not surprising. What's this convergence mean? Well, the semi-inner product induces a semi-norm, and we mean by convergence with respect to that semi-norm. What about over here? These are just complex numbers, so we mean convergence in convergence in the field of complex numbers. Proof of that, also not very long. Let's look at the modulus of the inner product of x sub n with y sub n minus the inner product with x and y. So we'll get something that depends on n in this, but it's just a modulus of a difference of two complex numbers. Let's do our usual trick of adding and subtracting the same thing, splitting those up using the triangle inequality. Triangle inequality where? This would be the triangle inequality for modulus in the complex numbers. So that's the triangle inequality in this setting. Here, we've produced inner product of x sub n with y sub n minus the inner product of x sub n with y. Hey, the first components are the same, first entries are the same, first variables are the same. Let's use conjugate linearity in the second term to combine those. Conjugation doesn't play a role because there's no scalars. In this one, we've added and subtracted cleverly, where here the second variables are the same. So we'll use linearity in the first variable to combine this difference as given. All right. Cauchy-Schwartz has something to say about this. Cauchy-Schwartz says the modulus of the inner product is less than or equal to the product of the semi-norms. And I guess I need to be saying semi-inner product still. I don't like that. Cauchy-Schwartz applies in this general setting of semi-inner products and semi-norms to introduce these inequalities here for both of the moduli of the semi-inner products. So we get this product of semi-norms. All right. Claim is if we make n big, we can make this small. And if you can do that, then we have this approaching 0, and that's the very definition of the first sequence elements approach the fixed second term. The x sub n, y sub n inner products approach the inner product of x and y. So let me talk you into, there's some details that certainly could be pasted in, but we've done lots of this. We know y sub n approaches y. So that can be made small. That was hypotheses. We know x sub n approaches x, so that can be made small. The gory details would be there exists a capital N sub 1 such that we can make this less than epsilon over 2. There exists a capital N sub 2 such that blah, blah, blah. This can be made less than, this whole term can be made less than epsilon over 2, say. My only concern is what about the x sub n's? And this gets little. Does that get little? No, but it's bounded. X sub n is a convergent sequence. Convergent sequences are bounded. We've stated several times. I could probably excavate the notes and find specific justification for that. I think we said it in a note somewhere. But the X sub n's being a convergent sequence is a bounded sequence. That's bounded. That gets little. That gets little. That's a constant. So we can make this whole thing little by making the index large, making lowercase n sufficiently large. And we could put this whole thing together with some capital N's. I probably need an N1, N2, and N3. But we could balance these, as we've done many times, and get this to be less than epsilon. We've shown this is less than epsilon for arbitrary epsilon. So it must be that this sequence is given approaches 0, and we get the claimed convergence. So notice this was called continuity of the inner product. It involves basically taking limits in and out of inner products. You want to take the limit of this inner product. We can take that limit inside the first and the second term, is what the claim is here. So that's the reason it's called a continuity thing. Continuity things tell you when you can take limits inside, be it inner products or functions or whatever. You take limits inside, it's a concept of continuity. That completes everything except the very last definition, which says, finally, a Hilbert space is a complete inner product space. That is, a Hilbert space is a linear space with an inner product on it. Inner products induce norms, so Hilbert spaces are normed linear spaces as well. And it's complete. Complete means Cauchy sequences converge. Informally complete means it doesn't have any holes in it, and so we can take limits and do analysis stuff. But formally complete means Cauchy sequences converge. So a Hilbert space, we have an inner product. It induces a norm. With respect to that norm, Cauchy sequences converge. So that's the foundations of what a Hilbert space is. The rest of this chapter is devoted to exploring properties of Hilbert spaces and looking at some examples of Hilbert spaces. And I say again, some neat geometry. In the best Hilbert spaces, you've got the same kind of geometric behavior you have in Rn. So the stuff you did in sophomore linear algebra, if you get the details mopped out as appropriate, Hilbert space will behave the same way as Rn. Those details involve bases and so forth, but we'll go through all of that in this chapter and in the supplements to this chapter. And that process is section 4.2. I will see you next time in 4.3 or maybe some supplemental material. Have a nice day.